So good evening, everyone. I am Shruti Pandey. I am a postdoc in IIT Madras, and I'm going to present this work, which is done in collaboration with Shubham Chakravarti, Anuradha Banerjee, and S. Ganga Prasad. So I will be starting the talk. So with peeling of a Velcro, this is something that we are very familiar with, but it is surprisingly complex also. So have you heard the sound that is there when you peel a Velcro? That is a crackling noise. So the question to be addressed is that are there any patterns or features that can be extracted from the crackling noise? So this is Velcro, and the image shows an instant of peeling. There are other systems that show crackling noise as well. One of them is earthquake. So people have studied and proposed this famous Gutenberg-Richter law, where the number of events when plotted against the magnitude of the events that is happening follows a power law distribution, which means the number of smaller earthquakes is more, while the large ones are rare but not negligible. This is a hallmark of a scale-free behavior. Again, power laws are often seen in systems that exist at criticality. Now in earthquakes, there are tectonic plates which have shear bands, which undergo failure. So now we can connect this directly to the failure of complex materials, where similar kind of emission statistics have been observed. For example, take another example, which is crumbling of a paper. When you crumble a paper and we measure the acoustic energy emission, we again observe this power law behavior. So what is common in all these systems? The thing is, these systems accumulate energy and then release it intermittently in bursts. So we are trying to address whether the crackling noise or the phenomenon that we observe in phenomenon can be treated via material failure theories. Again, the fracture models can be of two types. Like we can approach it from continuum point of view and from statistical point of view. In the continuum models, we have like Griffith's theory, where we measure the energy released, elastic energy released, and it should be greater or equal to the energy spent while creating the surface. So in these are deterministic models. But as we know, the real materials are heterogeneous. They have disorders inbuilt in them. So we will now follow the statistical approach, where we can encode the distribution of disorders in the material. So there is a classic branching process model in which when the system is at criticality, the crack may split into two, or it may remain on the same branch. So people have observed that the energy distribution follows a power law, in this case also at criticality, where the exponent is around 3/2. There are other models as well, like fiber bundle model with equal load sharing, which also follows power law, and the exponent near failure is around 3/2. Another model is there, which is the local load sharing model, where the load is not equally shared between the fibers. Then the exponent is slightly higher, which is around 5/2. So now I'll move to my experimental setup, and we will see that this is a Velcro. It consists of two parts, the hard part and the soft part. The hard part consists of hooks, and there are different hook geometries. This is mushroom, palmate, J-type, and tall J hook, where we have used tall J hook because this is the most common that we see in our daily lives. And the soft part is the part which takes care of the disorderedness in the material. Okay, it contains loops. So in our experimental setup, we have fixed the width of the Velcro and the length, and we are varying the peeling rate. So peeling rate is our tuning parameter. So we have simply peeled the Velcro and obtained the force response. So we see that it is not static. It's not constant, it's very much deviating. So each event is corresponded that whenever this detachment of hook and loop element occurs, there is a force drop which is observed in the force signature. So from this force signature, we try to understand the event extraction. So the force drop is the amplitude and event size is the amplitude of the fall times the duration of the fall, and we also extract the inter event time, which is the duration between two force peaks. Now when we plot the distribution of event sizes, we see that there is a large number of small events that is happening, and we see a clear cutoff. This cutoff is also dependent on the rate if we clearly see. So the cutoff is higher for lower peeling rates. That means for lower peeling rates, the number of small events that is happening is more. Then there is this scale-free regime, the parallel, where it follows the parallel distribution, and the exponent for all this rate is nearly 3. So there are two things that we observe. The first thing is that for all rates, the power law distribution is exponent is around 3. This is considerably different from the mean field exponent that is around 3/2. So our hypothesis is that this follows some kind of local load sharing model. And the second is that the cutoff depends on the rate. However, we expect the physics to be independent of the peeling rate in the process. So we tried this universal scaling collapse where we scale out the rate, and then we see that the collapse looks like this, which means that for intermediate rates, we can see that the collapse is nice. However, for small rates, for 1 mm and 10 mm, we see that it is considerably different. This suggests that there is some difference in the mechanism that is happening between slow rates and intermediate rates. We further kind of confirm this value, this thing, with the inter-event distribution that we have. So we plot the inter-event distribution, and when we see for lower rates, like say for 1 mm per minute, we find that there are two regimes. So there are two kinds of processes that may be happening. The first is the detachment process, and the second regime may be related to the relaxation of the material. So now we see that as the driving rate increases, the slow time scale is progressively suppressed, and it leads to a single dominant regime. So here we can conclude that Velcro peeling is a very simple system where we can see some rate controlled avalanche dynamics. These experiments are very simple, but the noise has some interesting features. And we observe a power law behavior which is different from the mean field theory. And the inter-event distribution, basically, initially it shows two regime behavior, but it finally reduces to one single scaling exponent. Now, these are the open questions that we have to understand. Like, why is that merging of two regimes into one is happening? So we are probing this through high-speed imaging and acoustic emission data. And what is the mechanism behind this? And finally, how do we derive the scaling exponents that would govern this process from local load sharing models? Thank you.
Can we have 1 or 2 questions, please?
In the data, why do you throw away the small drops in force?
Okay.
The next one.
Okay.
Yeah, these build-ups,
Yeah.
Let's also have zigzag.
Yeah, so this may be the noise. So this is a schematic. So when we measure, then there is always some noise in the data. So we have to be very particular about whether it is a noise or it's the event that is happening, because yes, we put a threshold. Cumulative probability distribution function. So avoid the binning effects and
Do we have any more questions? If not, I think we can thank the speaker.